Hello class, in this lecture we're going to first review everything before the midterm, and so I'll go over that now. And we're going to be following the same syllabus that was originally prepared at the beginning of the course, and so you can all follow along in your notes. But the things that we cover before the midterm, one by one, are light as a wave, which should be a review from earlier courses that you've taken, and the wave equation of light, which you know from Maxwell's equations is that the partial squared of E, the electric field, with respect to T squared, is proportional to the partial squared of B with respect to Z squared, which would be x and y in more than one dimension. And the proportionality constant is, of course, 1 over c squared. And the way I've always explained how you figure that out is that you look at the units and you figure out that I should put c squared here, where c is 1 over the square root of mu naught epsilon naught. And that comes from Maxwell's equations. So you can see from the units there that since c is velocity, that's meters squared per second squared, and you get the right units out of it. Now, the next thing we showed that from relativity, light is also a particle. And what we showed from relativity is that since as the speed of a particle approaches the speed of light, its mass increases to the point where at the speed of light it would be infinite, that a particle, the photon, with no mass moving at the speed of light has momentum, and that momentum, p, is given by h over lambda. And conversely then, what is argued and observed is that electrons also have a wavelength. And what that means is that electrons travel as waves. And what de Broglie did was he simply flipped these around and stated that the wavelength of electron was h over momentum, or h over mv. Now, just interjecting here for a moment, what we're saying is that everything travels as a wave. Meaning, as a particle, whether it's a photon or an electron, propagates through space, it behaves like a wave. When it interacts with anything, it behaves as a particle. Now, what's important here is that whether it's a light wave, or an electron wave, or a water wave for that matter, or a sound wave, it propagates as e to the I kz minus omega t. And that was the most important thing I wanted you to get out of that whole wave discussion, is understanding how to look at that equation and understand what the things like k mean. And so I'm not going to go over the midterm again. I did that in the previous video. But basically, you were supposed to understand how to relate k and lambda, that k times lambda, lambda is 2 pi, and that way this phase changes by 2 pi when you go 1 lambda distance, and that the velocity delta z over delta t is omega over k. So what's most important here is I want you to understand how to use this function for a wave, this wave function, and understand its meaning. All right, since we determined that electrons behave as waves, we have to come up with a wave equation and that wave equation was determined by Schrödinger to be Schrödinger's equation. And the main difference between it and the wave equation for light is that instead of the spatial derivative or being proportional to a second derivative in time, the spatial derivative is proportional to a first derivative in time. And the solution, if the potential is 0, is still e to the I kz minus omega t. In electromagnetic theory, we know to take the real part of this to get the real answer, which is cosine or sine. Here, this is the real answer. And in fact, generally, the solution of an electron wave, whether it's moving through space or moving through a crystal or standing in a resonator, is that it is a function of space and time, where the function of time is always e to the minus I omega t. And when you plug that into here, you get the time-independent Schrödinger's equation, which is that omega h bar little psi, which is d psi, is negative h bar squared over 2m partial squared of psi, and I'll start using x. And we use this equation to solve for the spatial function of psi, whether it's moving through space or whether it's confined in a crystal. Now, U for a crystal, or for a solid in general, is the way we describe it is that U is 0 inside and U is infinity outside. And then when we do that, it leads to the solution of K space, which describes that the solutions e to the I k, here I'll write it out, e to the I kxx plus kyy plus kzz, that when you plug that solution into the time-independent Schrödinger's equation, with the potential of 0 inside the solid and infinite outside the solid, it leads to solutions which are spaced by 2 pi over L. And there's the fact that they are spaced evenly in K space that leads to what we're going to discuss today in new lecture material, which describes how you figure out how many electrons or holes are in a solid. So we'll get back to that in a moment. Now, up till now, this is pretty straightforward modern physics and solid state physics. It gives you a solution for how electron waves or matter waves travel or are solved for. In principle, you can take the time-independent Schrödinger's equation and you can solve for it to get solutions. For example, if U describes the potential energy due to a proton, you can get the solutions for atomic energy levels and all those things, which we're not covering in this course. The important thing for us is that so far it describes this thing called K space, which is that when you have solutions that are K in each direction, that those allowed states are spaced evenly. Okay, and then the next step is we describe a potential differently. And if we describe a potential including the positively charged nuclei, so now we're moving away from just U equals 0 inside, but we're actually allowing the potentials of those positively charged nuclei to influence the electron. And we made this approximation that potential is this model that we do model as a square wave potential that leads to band structure. Where now, if an electron is at a certain energy E, that there are bands, there are ranges of energy over which there's no solution to Schrödinger's equation, and so there's no states. And there's ranges of energy where there's bands, like the valence band and the conduction band. And we showed how when you fold everything together here with K space in the spacing of 2 pi over L, it leads to that the topmost negative curvature band is filled with electrons, and the next band up has the opposite curvature, positive, and it is empty of electrons. Now here was where the second question of the midterm came in, because the most important result here is that E can be written as, for example, EC naught plus a proportionality constant, h bar squared over 2m star k squared. Going back up to here, if we plug the free wave function e to the ikz minus omega t into Schrödinger's equation, we get that E of a free electron is h bar squared k squared over 2m, the mass of a free electron. And so we get the result from solid state physics that an electron in either one of these bands behaves just like it's a free electron, as if it's moving through a potential that's zero, but with a different mass, the effective mass. That's determined by the curvature. Now, going back to the midterm, and again, I went over the midterm in the previous video I put out, but a lot of you didn't quite follow that that's C naught or whatever coefficient I said, and instead you did something a little bit convoluted to try and equate this proportionality constant with m star. And so I ask you to go back over that video if you still don't understand how to come up with m star. And then somehow contact me over email or, as I've discussed, phone, if you still need help figuring out how to determine what m star is. For example, I could give you values of E versus K. And so useful exercise, perhaps a good idea for this week's homework, is to give you actual values of E versus K for both the valence and conduction band, and ask you to come up with m star from those values. All right, so we're still before the midterm. Now, the next thing we did was we talked about doping of atoms in a crystal. So, for example, this picture would be for a pure crystal with no impurities. And in that picture, for example, of silicon or gallium arsenide, the valence band would be completely filled, the conduction band would be completely empty, and the solid would be non-conducting at 0 Kelvin, because a filled band cannot conduct, because the electrons can't change state, so they can't move. Of course, an empty band cannot conduct. And so in order to make the solid conducting, we have to somehow move some electrons into the conduction band, or move some electrons out of the valence band. Now, one way to do that is to heat up the sample, and so if you heat up the sample to like room temperature, there'll be a few electrons that go up to the conduction band, and so make them conducting. Or you can dope with donors or acceptors to make either N-type material or P-type material. So along those lines, let's go back over here and start to get into some more detailed discussion of what all this means. So, let's redraw our band structure. And I'll try to draw a little bit bigger and make this a little neater now, because now we're getting into the real important parts of the course. So let's draw our valence band and our conduction band. And the way we explain this, okay, so let's first jump ahead to the result, as I told you before the midterm, in which I was glad to see that I think everyone pretty much, or almost everyone, remembered, which is that there's a density of electrons in the conduction band, and that's N, and there's a density of holes in the valence band, and that's P, N and P. They have units of 1 over volume. And what I told you for the midterm and what we'll start to prove today is that N times P is always equal to something called Ni squared. Now, if a sample is undoped, pure, what's going to happen is that a few of these electrons will go up into the conduction band from thermal energy. Now, what you see here is that they have to be equal in that case. Meaning, if a semiconductor is pure, there's no doping, it simply is at an elevated temperature, so there will be an N and a P. All right, N is equal to P is equal to Ni, the intrinsic doping level, or carrier level. And so that's pretty simple to understand. Now, what is Ni? Well, that's kind of complicated, and we're going to try and figure that out today a little bit. Now, so we said that N times P is equal to Ni squared, and no matter how you dope the sample, and that's clearly true if the sample is undoped. All right, now, you know, we're going to start to cover how you calculate Ni today. But one thing you can kind of see already is that Ni depends on temperature and goes up as you increase the temperature. Because at 0 temperature, Ni is 0. Right, at 0 Kelvin, none of these, there would be no thermal energy. And so there would be no holes in the conduction band. They're drawing them as holes. And there would be no electrons in the conduction band. So Ni increases with temperature. Where of course T is in Kelvin. Okay, now let's say we dope the sample. All right. So this would be undoped. Now let's say we dope it with donors. Now, as I explained before the midterm, a donor impurity introduces a state in the band gap because it's essentially a defect in the crystal. Remember that if there are no defects in the crystal, the band gap is pure. There are no states in it. But if we have some defect, like a crystal dislocation or something like that, then there's a defect level, and the defect level of a donor state is near the conduction band. So because a donor has an extra valence electron, and this spacing is so small, it just takes a little bit of thermal energy and you get that electron from that donor state in the conduction band. Now, if a semiconductor is doped n-type, it's going to lead to a lot of electrons in the conduction band and very few holes in the valence band. And the result is still that MP is Ni squared. So this equation means that no matter how you dope it, and this would be n-type, if I do p-type, the opposite happens. I have a state near the valence band, and it leads to a lot of holes and just a few electrons. And for both, n times p is a constant Ni squared. Now, it's perhaps a little bit non-intuitive that this would be true from the pure case. All right, the pure case indicates that with like room temperature thermal energy, I get some electrons in the conduction band and some holes in the valence band. And now I'm saying that if I dope it n-type, it leads to a lot more electrons in the conduction band, n is higher. But at the same time, there will have to be fewer. The electrons in the conduction band. There has to be fewer holes in the conduction band, or valence band. That is, P has to go down. Now, that's perhaps difficult to understand just intuitively. Why, if I dope it n-type, the number of holes has to go down. You can easily understand why the number of electrons has to go up. Same thing for p-type, all right? From the pure state, if I dope it with acceptors, all right, those acceptors accept electrons from the valence band, making holes in it. Of course, it's sort of easy to understand why, if I dope with a lot of acceptors, I have to get a lot of holes, but perhaps not as intuitive to understand why, okay, that leads to fewer electrons, all right? But what I'm saying, without proving before the midterm, is that regardless of how you dope it and at what level, this equation holds. Now, that led to the third midterm problem, which was to figure out things like N and P from charge neutrality. Charge neutrality says that plus equals minus. And on the plus side, you have, of course, the holes. And on the plus side, you have the donors. Because when a donor atom gives up its electron, it leaves behind a positively charged ion. And on the minus side, of course, the electrons, and plus the acceptor ions, because when they accept an electron, they become negatively charged ion. And furthermore, I told you that in this course, we would assume that the ionized acceptors, meaning the acceptors that have accepted, that are existing in a state where they've accepted an electron and so are negatively charged, is roughly equal to the density of acceptors, meaning every acceptor is ionized. And the same thing for the donors. Now, what that is saying is that we are assuming that this energy here and this energy here are small compared to the thermal energy. Now, in an advanced course in solid state devices, you can run into situations where that's not true. But in this course, we're going to assume we're always in a situation where that is true, that every donor atom has lost its electron, and every acceptor atom has accepted a valence electron from the valence band. All right, and so we can write that P plus ND is equal to N plus NA. And then we can use this to solve for NRP as we did in the midterm. And so I won't go through that again because I did it in the video where I went over the midterm. If anyone has any questions about that, they can get to me. But it's pretty simple when you think about it to solve for anything. Now, we furthermore then solve for the conductivity and things like that, and we'll go back to that when we do MOSFETs toward the end of the course. Now, now we start basically with new material. And the first thing we have to do in the new material is we have to prove this. And the way we do that is with the Fermi energy. Now, we haven't talked much about the Fermi energy yet. When we covered K-space, we sort of referred to it a little bit. We described the Fermi energy as the energy of the highest energy electron in the material. And that's sort of true, but not really a proper description. And so what I'm going to do now is I'm going to start referring to the Fermi energy with respect to the band structure that we derived. Now, I don't have a drum in the right place, but let's imagine for a moment that this one was the undoped case. Now, in the undoped case, we showed that at t equals 0, all the electrons are in the valence band, and there are none in the conduction band. Now, from my sort of qualitative description of the Fermi energy, you might think that that means that this is the Fermi energy, because that's the energy of the topmost electron. Now, to a certain extent, at t equals 0, you might say the Fermi energy is undefined. But that's, in an asymptotic case, as I'll show, not the right way to think about it. And it's because the Fermi energy is really defined by the Fermi-Dirac function, which is that the occupancy F of an electronic state is given by 1 over 1 plus E. Now here, it's always helpful when you write this to think about the fact that the occupancy of a state has to go down with energy. Now that's if we're talking about electrons. We'll get to that in a second, but for a moment that's what we're talking about. So when you write it down, you know, you can forget whether it's E or EF. It's E, because that's in the denominator then, and so that means that F is going to go down with E, if you look at it. Now, what this function tells you is that, first of all, the occupancy goes down with energy, and it's equal to 1/2 at E equals EF. Because at E equals EF, e to the 0 is 1, and so 1 over 1 plus 1 is 1/2. Okay. Now, kind of picturing all that, and let's imagine that this one is let's imagine for the moment that this is the undoped case. At t equals 0, we would have that the occupancy is 1 for the valence band, or for energies lower than the 0 of the scale that I put there. And if I draw the conduction band, it would be 0. Okay, so that's pretty clear. I mean, I just defined F. I didn't need the Fermi-Dirac function, I just needed common sense. At t equals 0, it's 1 for the valence band, and it's 0 for the conduction band. Now, as I said then, at t equals 0, it's sort of undefined in this middle region in the gap. All right, but what we're going to do is we're going to sort of use common sense and say, well, EF is kind of in the middle. Now, we might go through a few details later on where EF will show that EF is not exactly in the middle, but for now it's about in the middle. And so we're going to draw the Fermi-Dirac function at t equals 0 then like this. Where this is the bottom of the conduction band, and this is the top of the valence band. So, you know, in terms of using the Fermi-Dirac function at t equals 0, we could have put EF wherever we wanted. All right, but I'm saying because of the next thing I'm going to do, which is I'm going to raise the temperature, it makes sense to put it in the middle of the band gap. Because now, if you look at this function, okay, this function, you can, if t is very small, or very, you know, 0, right? If E is above EF, then this is E to a very, very large number, or infinity, and 1 over infinity is 0. So as long as at t equals 0, E is above EF, it's 0. If it's below EF, then this is E to negative infinity, and so it becomes, this goes to 0, and it becomes 1 over 1 or 0, or 1. Now, this is at t equals 0. Now watch what happens when you make t finite. You make it non-zero here. Now what's going to happen is that it's always going to be 1/2 at EF as I raise the temperature. but this is what it looks like. So this is for T not equal to 0. And I should have drawn it a little bit nicer. What you see is that here, there's this non-zero tail, and the same thing here, I would have drawn it better, that there's this non-zero tail here, and they're equal. So when I went from T equals 0 and I raised the temperature, it means that the occupancy of electrons went up by the same amount above the conduction band bottom as it went down below the valence band bottom. And so N and P are equal. Okay, let me just stop for a second. Now, the Fermi-Dirac function describes whether it's probable that a state is occupied or unoccupied. And so the position of EF tells us whether we're going to have more electrons or holes. So let's look at that. So this would be undoped. Now let's use the actual p-type. So I'm using the same scale where this is the bottom of the conduction band and this is the top of the valence band. And now here is when in class I would I would ask someone to tell me, okay, this is undoped, and this is now p-type. And I would ask someone to tell me, okay, for p-type, where would the Fermi energy now lie? And hopefully someone would answer, it would be closer to the valence band. Because now, okay, let's go first from for our zero temperature case. All right. So now if we put EF closer to the valence band, now what's going to happen, okay, you always start at 1/2 at EF. Let me try to draw it a little bit neater. All right, now I can sort of start to draw now the indication of how many holes there are. And you see it's indicated by the fact that F is less than 1 down here by quite a bit. F is greater than 0 up here by a very much smaller amount. And you can see that as I move EF around, so N becomes bigger up here and P becomes smaller, and N becomes smaller up here and P becomes larger. And so the result of that is that the product of NP is always the same. So the first step to understanding my assertion before the midterm that n times p is always equal to ni squared is to look at these pictures with the Fermi-Dirac function and move the Fermi level around in the gap. And that sort of shows you qualitatively, at least, that when I'm undoped and EF is in the middle of the gap, n equals p. If I make it p-type, that moves the Fermi level down closer to the valence band. And now p becomes bigger, n becomes smaller. And so if I move it down, n becomes smaller, p becomes bigger. If I move it up, n becomes bigger, p becomes smaller. And so their product, at least it looks like qualitatively, and will show mathematically, is the same. Let's see if we can do that a little bit more neatly for the n-type case. Okay, so let's make it a little bit bigger. So here's E versus K. All right, there's my conduction minimum valence band. And let's draw the Fermi-Dirac function. And let's put EF in the middle, meaning undoped case. And so this is the bottom of the conduction band. And this, of course, is the top of the valence band. This is 1. EF is in the middle. And let's first I should get colored chalk for this. Let's first do t equals 0. Now, this is t equals 0. Now what I'm going to do is I'm going to raise temperature, and I'm going to sort of exaggerate it a little bit. Now, what we went through is that at E equals EF, it's always 1/2, no matter what you do. No matter how you change the temperature. And again, that's looking over here and seeing that if E equals EF, no matter what the temperature is, okay, that's 0. And so e to the 0 is 1. 1 over 1 plus 1 is 1/2. Now what I'm going to do is I'm going to draw the function sort of exaggerating things a little bit. And try to do it carefully. So this is t not equal to 0. And you can get, I mean, you know, you could plot this on a computer and just show that. how much of this curvature there is depends on what KT is in EF and things like that, but you could plot it out. And so what you see is that if EF is in the middle, which is undoped, the occupancy of the conduction band and the unoccupancy of the valence band are equal. So the number of electrons, N, is equal to the number of holes, P, because the function is symmetric, because I put EF in the middle. All right. Now, I haven't told you yet how to use F to calculate N and P. We're going to do that next. But you can sort of see that since F is symmetric, they will equal each other. And again, that follows from the fact that it has to be the case that if by thermal energy alone I move an electron from the valence band to the conduction band, there have to be the same number of holes left behind as electrons up here, because that's what an electron does, is it leaves behind a hole. Okay, now let's do N-type. So I'm going to draw my conduction and valence band again. Draw E versus F. And now what I'm going to do is I'm going to put EF closer to the conduction band. Now here you may say, okay, how'd you do that? Well, I did that by doping the material N-type. And then you may be saying, well, okay, but I don't see the connection. You know, how did doping the material N-type move the Fermi energy closer to the conduction band? Well, the answer is, as you know, when we complete the whole analysis and we use charge neutrality to determine N and P, and also make it equal to what Fermi direct statistics tell us it must be, you will see that in order to have more electrons and holes, I had to move the Fermi level up. Okay, let me say that a different way. Okay, when I dope a material N-type, all right, what it means is, I mean, sort of commonsensically, is that if I dope it with donors, I'm going to have more electrons and holes, right? Just sort of makes sense. It's not perfectly clear why, because you put in donors. I mean, it's clear why the electrons went up. Why the holes went down, well, maybe that's not so clear yet, but it did. At the same time, the occupancy has to obey the Fermi Dirac function. Now, why is that the case? Well, for that we go all the way back to quantum mechanics, and you know, we force the fact that an electronic state can only have one occupancy, two if you include spin. And so, you know, it's forced by, it's called the Pauli exclusion principle, which tells you that you can only put electrons, 2 electrons in each state. And so you can't put them all at the bottom, they have to stack up. So, you know, we're engineers. We covered enough quantum mechanics so that you can kind of follow what I just said. But as engineers, we'll accept that this determines the occupancy, where EF is the Fermi energy. All right, now, so because the distribution has to obey this, and because then that means that if I dope it and if I put in donors, if I'm to get more electrons, EF has to move up because the occupancy of the conduction band has to go up. Okay, it can't help not going up. So let me write that down over here. If I put in donors, okay, if I put in donors, N has to go up, right? Has to. But in order for that to happen and obey the Fermi Dirac function, EF has to go up. And because of that, P goes down. All right, so let's draw it out. So the way to think about it is, okay, I put in donors. EF went up from the middle. Now, right, let's draw our Fermi function. The way you do it is you first do it at 0 temperature. Then, at the Fermi energy, it has to be 1/2. Now let's see what happens. I'll try to draw the curve the same way I drew it there. That's kind of close. All right. I didn't do a good job. Let me try and make it a little bit more the same. I mean, basically what I'm doing is I'm shifting this curve up. And if you try to imagine I did it right, that would go bigger. And this would get smaller. So P would go down and N would go up. Okay, so the lesson today, the main lesson today is if I put in donors, EF goes higher. N goes up. P goes down. If I put in acceptors, EF goes down. N goes down. And P goes up. And just to make clear, I mean, EF goes higher means it gets closer to conduction band. And EF goes down means closer to the valence band. And if I put those two things together, what I'm going to show mathematically next is NP remains the same. If I put in donors, EF goes up, N goes up, P goes down, but their product remains the same. And the same as I put in acceptors. Now, why is it equal to Ni squared? Because at zero doping, it's equal to Ni. Each one is equal to N sub I. So, I've at least shown you a little bit more, at least qualitatively, why that's true. All right, now, the next step is to figure out what, so I'm going to erase this part here because I'm going to start putting in equations. Now, let's say I do this, okay? How do I calculate N and P? All right, now, to do that, we have to introduce something called G sub E, which is the density of states. Or the states per unit volume per unit energy. Now let's first show how you use G here, and then try to explain more what G is. All right, so let's go over here. Now, what is N equal to? N is equal to, at each energy, I have F of E. Right? That's the Fermi-Dirac function. That's this function here. It goes between 0 and 1. And so, at each energy, I have a certain number of electrons per unit volume. Now, at that energy, so what I'm going to do is, let's write it this way, let's put N of E, or the density of electrons at a certain energy. Now, it's not equal to F of E, because F of E is just tells you whether the state is occupied or not. Okay, if it's 1, it's always occupied, 100% of the time. If it's 0, it's not occupied, so it's something in between here. What we have to now multiply that by is the states per unit volume per unit energy. That's G. So then N is equal to the interval from the bottom of the conduction band to infinity of N of E dE and so that's equal to the integral from EC naught to infinity of f of e, g of e, dE. Now, all we're saying here is that, okay, we're going to figure out what n is by integrating for every energy position the density of electrons at that energy. And that depends on two things. That depends on F, which is obviously going down as I go up in energy. And it depends on something I'm calling G, which is the number of states at that energy position. All right, so this is the integral we have to perform, but first we have to determine what G is. So I'm going to erase this for now, and we're going to end this lecture by me telling you what G is. So, for that, go back to K-space. I told you it was going to come in handy, and now's when it does. And it does because the fact that K is spaced evenly, that states are spaced evenly in K-space, that we can determine what G is. Now, what I'm going to do first there is just show K-space as some arbitrary So what I want you to do now is I want you to go back to our K-space discussion. Forget about band structures or conduction bands or valence bands for the moment. Just go back to our picture of the electrons piling up in a semiconductor sample or semiconductor sample, where we just assumed that this was this model where inside the sample U equals 0 and outside U equals infinity, and so that that led to the spacing in K-space. Now, what that means is that, okay, it's always the same, that h bar squared, and now we write kx squared plus ky squared plus kz squared over 2m is E. So, I mean, remember when we covered this in that lecture, what that means is that when I draw K-space, inside of a sphere in K-space, those states are filled. And outside they're empty. All right. Now, at a certain energy, we're going to have a K radius. And G is the states per unit volume between between E and E plus dE. So if I have, now, okay, so let's think about this for a second. Okay, E is h bar squared k squared kr squared over 2m. So that defines an E sub r to this surface of a sphere. And now I'm going to make the sphere dE bigger or dkr bigger. All right, and I want to find the number of states in that little shell. And that tells me what the density of states are, G of E, at a position E. All right, so let's just walk through it. So G of E then is equal to the K volume over the K volume per state times 2, because remember, spin up, spin down. Now, what is the volume of a spherical shell? Now, there's different ways you can think about this. Offline, maybe you can do your geometry. One way to think about it is to take the volume of a sphere, 4/3 pi, and take kr plus dkr cubed. That's the volume of a sphere, 4/3 pi r cubed, and subtract off 4/3 pi kr cubed. All right, and figure that out. You know, now the simpler way to think about it is the volume of this is equal to the surface area of that times dkr. Now the surface area of the sphere is 4 pi kr squared. So, I mean, you can get that from doing this. This is the volume of the shell plus dkr. Why don't we do that? We don't need this anymore because we're going to get back to this on the next lecture. I'm going to draw two spheres here. I'm going to try and make this one a little bit smaller. Okay, so I'm drawing two spheres in K space. One has a radius K sub r, and one has a radius K sub r plus 4 plus dkr, where dkr is the differential change in K. So the volume is 4/3 pi kr plus dkr to the third power. Right? 4/3 pi r squared. I'm not going to prove that. You can look that up. All right. So that's 4/3 pi times, let's first multiply two of them. So I'll do kr plus dkr. All right, so I'm going to take the square. Kr squared plus 2kr dkr plus dkr squared. But that's 0, right? Because if you take a differential and square it, it goes away. So then that's 4/3 pi times, now multiplying these out, so you get kr to the third, all right, plus 2kr squared, right, that one times that one, dkr, all right. So I took kr and I multiplied times those two elements that remain. Now I'm going to add this one here, plus kr squared dkr, right? That's this one. Now this one goes away because, again, if you have dkr squared or whatever, it goes away to 0. Okay, so it's 4/3 pi times kr cubed minus 3 kr squared dkr. Now, this one, right, is just 4/3 pi kr cubed. All right. Now I'm going to take this one minus that one. That goes away, and you simply are left with 4 pi kr squared dkr. So, you know, I mean, you can show it that way, but the simpler way to think about it is the volume of this shell is simply the surface area of that shell times its thickness, dkr. All right, so that's the K volume we're interested in. That's the number of K states between E and E plus dE. The K volume per state, remember, right? You get that by drawing a box around each one, which is 2 pi over L on the side. So that's 2 pi over L cubed. So that's equal to L cubed over pi squared, 2 times 4, that erases that one, kr squared dkr. All right, now, what I said I wanted is we wanted the states between E and E plus dE. Well, the way we get that is because E is equal to h bar squared kr squared over 2m. And so dE, taking the derivative, is h bar squared. With the 2, that cancels that. Kr dkr over m. And so we can solve this one for kr. That's the square root of 2me over h bar. And we can solve this one for dkr, but it's sort of simpler to solve it. Kr dkr is equal to m over h bar squared dE. So plugging that in here, if I haven't made a mistake, G of E is equal to L cubed over pi squared times KR times KR dKR. You can see why I did it that way. Over pi squared, KR is the square root of 2ME over H bar, and KRT is M over H bar squared dE. Now, the L cubed may look a little problematic here, but I sort of have done this in a fuzzy way because remember what I said, what we wanted really is the states per unit volume per unit energy. And so really, you know, I should have been labeling this sort of as GE prob as the states per unit energy. States per unit energy. Whereas G of E, the states per energy per volume, you just take out the L squared, L cubed, because that's the volume. Now, I'm not going to simplify terms at this point. I'll do it in the next lecture. But the point is that in K space, all right, now again, we're going back to this model that didn't have bands and stuff like that. It just started at E equals 0. It means that the density of states goes up as the square root of E. Now, you can sort of see that because as my sphere gets smaller, you know, as E goes down, this shell is getting smaller. And so the K volume is getting smaller. And so eventually, when I go down to 0, G of E is 0. There's no states. All right, we're going to stop here because the next step is, okay, we have to explain how this G of E thing works when now you have conduction bands and valence bands and things like that, which is very simple. First of all, you know one thing already. You know that we're going to replace M with M star. And the other thing is we have to understand, you know, that E now starts at the bottom of the conduction band. So next time we'll sort of review this a little bit in the context of now drawing K space with, you know, with regard to bands. And I'll figure out how to do that best. And then we'll do that integral of G of E, F of E, and calculate what N is. And then we'll calculate what P is, and we'll show that their product is always a constant. Okay, so that'll be in the next lecture.